Today we're going to be looking at a DAC, the 8562 by TI. We're looking at this today on how we can write a driver for it, as well how we can interface with it. The problem I see currently is that it's quite difficult to find information on certain things related to embedded and how we can certainly improve them and implement them. So I'll be doing this from scratch, from using the STM32 Cube IDE. In the Cube IDE, we, as you might know, we're usually greeted with this page where we can configure our pins and it auto-generates the code for us and does all that stuff. So here I've already set it down below. To do this, I know the DAC 8562, we can communicate over SPI. If we have a look at its datasheet, we can see that it's a dual DAC. It comes with 16, 14, 12-bit versions. It has with 2.54 internal reference, so we don't need to play a reference to it. And just based on the description itself, that we can interface compatible with standard SPI, QSPI, microarray, digital signal processor, DSP interface. In this device we see here, we can look into it and we're looking for something, well, how do we start writing this driver? What do we need to do? What can we do? Of course, I know what I'm looking for, but if you did not know, you would read through this entire data sheet and the key parameters. One of the important things that I had struggled with to get with was understanding this feature here for the pins. So sometimes datasheets are not as clear as what it is, and we need to pay a bit more attention to it. They might not say explicitly, but it does say later on in the datasheet. The two pins were the clear, which is a active low. So it says on the activation, clear 0 scale of this model of DAC or mid scale is loaded to all input in DAC register. This sets the output voltage accordingly. Okay, and this LDAC is used as a negative edge trigger signal. So we can use this to, it looks like if we wrote multiple commands and then we can make them fall on the LDAC pin to update register simultaneously. So we can update everything all at once. As compared if we put it to synchronous mode, we can tie this to ground and we can have the clock update the register, or when we're finished writing our command to it. When we go down into the device, to the detailed description of the device, it gives us a much more comprehensive overview of how this device actually works. So what can we do? So we can see that we can get a full range scale output of 2.5 or 5 volts. For us personally, I'll be showing you to use the internal voltage reference, which is 2.5, how we can configure that. The output of what our expected Vout is, if we've inputted our code, how this DAC is actually working, seems to be a resistor string, the output amplifier, the more details internal reference, and what we can do and configure on its power on setting. If we look further into it, so if we go to programming, it tells us a bit more on how we should actually program our device. This is where you would get most of the information. So the normal write sequence, it's a standard, we can use standard SPI with it, and we can know that when we bring the clock low, we know we can start writing to our device. So we bring it low, then we start writing it. So if we bring this up high, it seems invalid because we've brought it high midway through. But if we bring it low, held it low for the write sequence, bring it back high once we're done writing, and we can see that it falls on 24 falling edge. So it even says here stays at low for at least 24 falling edges of the clock signal, and then afterwards, then it updates itself. If it's brought high before then, it'll act as an interrupt to the write sequence. So we could actually think that if for some reason we wanted to change our value, or maybe, I don't know, maybe for some reason there needs to be some fast change, we could interrupt it and we could cancel it out. But overall, this is how it would work. This is where we'd start actually writing a command. So we are given a few commands for what we need to do. So we've given a few to say that on bits 23, 22, it's an ignore, we don't really care. It decodes the next 3 bits to determine the operating control mode. So we see if these commands, what actually are we doing with the command itself? What are we asking the DAC to do? And the next part is the address. So which DAC are we referring to? Are we referring to DAC A, DAC B? Are we referring to the gain? Or are we referring to both? The following bits are then the data bits, so this would be when we insert the actual corresponding bits for our targeted output voltage. As you can see here, we're given this data structure here, or this format, which we need to pay particularly close attention to when we start working with this. We're then given the command matrix below. So ideally we could define all these and make a register, so we give ourselves full capability by I'm trying to make things a lot more simpler, as you'll see later, in that I've included both the command and the address line to make up 1 byte of data. So we include it, and then we just have the rest of the 16 bits makes up 2 bytes of data, which we can place into and send through our SPI chain. This allows us, if we put everything all into one command or 1 byte, we don't need to do anything else. It makes things quite simple and easy to modify and move and use. So this is where you get all the information in according to what you need to set up and write your driver. We know that it communicates over SPI. We have the registers that we need to write to. We have a basic idea of what we need to write and how we're going to do it. As well here, this gives us a sort of reason of what we need to do and set it up and so forth. So we have all this here to our micro over in the STQ IDE. We see that we have set up our SPI peripheral. So if we click onto SPI1, SPI1 hot mode and configuration. So what we need for SPI, we need a clock, we need a data signal in, and we need a GPIO to register we're speaking to this first. What we need to do here is understand, well, okay, we need these pins. So if we put as the full duplex master, we see that we get the full SPI, well, the 4-wire capability, that we have the master input slave output or master output slave input. So, but for this purpose, we don't need it, so we can change it down to half duplex master. Of course, if you had other peripherals on this bus, then you would implement that, but for this case, we don't need it. Frame format, we can keep standard with the most rollup, and data size 8 bits. We're keeping it to 8 bits for now. We don't see any reason to. We could increase it for what we need to transfer, but we're doing it 8 bits at a time. This is most important, that make sure you have this selected as most significant bit first. If we go back to our data sheet, we can see that it implements the most significant bit first. As we see here, DB23 most significant bit first is the first bit that's loaded into the DAC shift register and is then followed by a 24-bit word pattern. So this gives us a much more further detail into how this actually works out. So once we've set up this is quite generic. I just have the USART pin enabled so we can do some print, so we can see in the print or debugging. We can click save and generate our code. This has been generated before, but we'll just say we'll generate it and nothing else has been really added into it. So we have all this commenting and whatnot has been given to us, all this standard thing has been assigned to us, and what we can do now is actually use the driver we've made. So if I've loaded up the DACs, so we have a source file, a header file, and the source file is typically where you would put all your functions in, what do they actually do and such. So we have that all implemented within here, and the header file is where we've defined all our addresses, what it is, and as well our functions itself. It may look a bit daunting at first, but I will leave the repo inside the description where you can download it for yourself, but it really isn't all that bad. But let's start with the header file. So I've included what the standard libraries I need here. I don't think I need the HAL for this because I'm not using it, so I can get rid of it. What I do need it is in this file here, so we can use it. If I build it, we get 7 warnings, and it's just a bunch of sort of things I'm not using. I should need to include math.h because I'm using a round function. But if we go through here, as you can see, I am writing each register for what has been given to us. We bring back up our data sheet. We can see here 00x0. So I'll put this to one side. We can see 0x00. We have write to input register n, 00x1 software LDAC, and you may be thinking, why is it not 0x01? Because you have to think from the most significant bit first, as well how many bits you're actually writing from. A helpful website I use is this binary to hex conversion. So when I was writing all these, what I did was I went to here, and we see, if we remember, it was 0001 software LDAC. So we have software LDAC, and we can update the register n. So if we follow this here, we see the first 2 bits we don't care. So we don't really care. We can assign them 0, 1, 0, 0, whatever. It doesn't really care. But it looks for these next 3 bits here. So following this structure, here, bits 21 to 19 is 0, 0, 1, 0, 0, 1, and that's it. If we put here, it is a 1. So you could put it like this for your command, but I've put everything even with the ingress inclusive. So if I put the ingress inclusive, we get an 8. So this makes up our 2 bytes of data. So this is how we get the 0x08 on here. This follows a similar pattern for the rest of the registers following down for the command line. So let's do another one. If we say write to register input n, or maybe software reset 101 again. So don't care bits 101, and our address bits 0x28 we have here. So we can actually pass this through. A lot of the times is that when we do something like a software reset, you could see that these bits don't care afterwards, and we just have the particular data bit at the end which we'll need to pass through. But again, for these things like this, you may want to keep the command and the address separate if you want that flexibility, and combine them together and issue that command. But of course, it really is dependent. In this case, I have just commands for use. I've just included the address in them. So for example, if I wanted to write so let's say the command DAC gain set is 0x02. I would look here. I'm looking for the gain set, the command gain set. So I've looked here. Don't care 00010. Okay, don't care 000010 gives us a hex of 2. Again, let's say if I wanted to write command write DAC A B register, I would look at the command matrix. So I'm looking for I want to write to both DACs A and B. This is a 2-channel DAC. I'm looking for it. Okay, here it is. Write to DAC A and B input register 0x07 00. Don't care. Command 1117 0x07. So now that we've understood what we're doing here to get these registers, and it follows the same kind of pattern for all these different values. So again, once we have it over here, let's say the data, let's say something specific such as gain set to, let's say gain 1. So gain 1 for both, so for both DAC B, DAC A, it's again, we have 16 bits, 4 bytes worth of data. We have 00000 all the way up. So if we do that full conversion, so it is 1 1 on bits 1 and 0. So 1 6, 15 14 13 12 11 10 9 8 7 6 5 4 3 2 1 0, and gives us a hex value of 3. We can see the bits here. It gives us a more overview. So we have don't care all the way up to bit 2, so bit 15 to 2. We don't care. We can have different values, and then we have 1 1 for the 2 on the end. It just looks at these in particular, and that's how we do it for that. So once you've laid out all these kind of registers, and of course this is universal for any sort of peripheral you may deal with, it's not this DAC specific, but it is more in general how we're writing this for an STM32 application. You can see here that I've got a few commands that I've returned a uint 8, and this is for the status, and except this one, I'm not using this one at the moment, but we have a few commands for what we think it will be most interested for us. So we have the begin, so this is all our peripheral initialization, the gain set, the D in calcs, so what is the wanted voltage you want, and what's the D in, and calculate that for you, what's your gain, your VREF. It's quite universal for someone that wants to use. You of course tweak this for a more generic approach, I guess. Generic write register, so it's DAC A, so write to DAC A specifically, not update. You can update them, or you can write and update, and power up, power down, reset, update, which clears off everything. So let's start this off. So I start this off in initializing my DAC here using this command, and I'm returning having a status. So we get the status from these functions themselves. We keep checking. We can do a bit more error checking as we don't know which status has failed really, and all we're doing is each one will get rewrote on top of each other, so we can actually improve that a bit. But for now, let's do it like this. So we're resetting the device. If we go into this, it'd be good to put like a little feature on what this does. If we go to our data sheet, we see reset all register, updates all DACs, power on, reset, update. So it'd be good. Reset all registers and update DACs. Just good to know what we're actually doing with this. So in this case, this was me before trying to debug and everything. We don't need it for here. So with our buffer of array of 3, initialize uint 8 because we are expecting 2 bytes, so we can hold up to that. We have the command software reset, which is a known thing, and then we have our data expansion. So 0001, we are right shifting this by 8 to retain the lower, to effectively move it to the lower 8-bit, and then using a operator of AND of 0xFF, which is essentially 4-1. So 0xFF is as so. And all this does would mask out any bits beyond the lower 8 bits. So we retain our data as it's expecting, again, the most significant bit first. And so coming over here, what we need is just the lower 8 bits from this value. So we have extracted the upper 8 bits from here. So we've extracted the upper 8 bits from here and got rid of the rest. And for this one, we are just extracting the lower 8 bit from what we've said here. And this effectively in this TX data will give us our entire 24-bit word format that we want. And what you should see upon sending, or what the microcontroller should see, what the device should see, is that if we should see that, so that's the command, the don't care bits, and the address bit. So if we put it like that, and then we have the 0000 0000 0000000001. This is what we are sending as our total word format. It's a bit funny, but this is data, address, command, don't. So this is what we're sending and passing through our HAL SPI transmit, which is the standard polling function, or in blocking mode, in which it's quite the easiest to set up, so that's why I'm using it here. And what this does, if you're unsure of where to find these, as I did, I had quite a few issues upon starting it. If you had a few issues with searching out and what the API and the HAL is sort of what you need, you can generally find it by searching HAL and your given microcontroller documentation. This should lead you to a description of the HAL and low layer drivers provided by the manufacturer, or ST in this case. And it's quite a lengthy document, and usually what you do is go search. It has all the different peripherals and what such you can use. But if we go to, since we're using SPI in this case, we can go to SPI and we can see how to use the driver. It gives us quite a comprehensive description. So for this, in this case, we are just we're not using DMA for this case, but if we just go down, so we can initialize the SPI function here, and if we go down, it tells us the following APIs. So this is what I mean. Blocking mode is in polling mode, and there's non-blocking modes. We can put it in interrupts or DMA. But then we can go down to here and we can see all the functions which we can use. So we can use transmit, and this is what we're using to send out. And if we were using the full duplex master, we could use HAL SPI receive to receive data from our peripheral. Or instead we can use transmit, and if we're expecting something out, we can receive it back. But before that, we need to reset the NSS pin, so our set pin low, to initialize the SPI transfer, to say we want to speaking to this peripheral. We are transmitting the data, is passing through the handler. What's the data we want to send? So we are sending from the TX data portion. What's the size of this? So we could use the size of to clearly define what is it. And we're just putting the max timeout we can. If this equals HAL okay, so everything equals okay, this will return true and our status will give us a 1. So we do this all for the rest of our functions going through. This whole entire driver follows a similar format for each one, as you can see. If we go to our code here, we can initialize our code. So we can put DAC begin. We can say that. Yep. To initialize our DAC, what also we are wanting something to calculate D in. So we can say under D in, we want to give this a type, and then now we've initialized our DAC. We want to say calculate D in calculate. So what is the voltage out? So let's say we want 2 volts. We have a gain of 1. Our VREF is 2.5. And we can return this value, as if we look through, this returns a rounded version of our DIN calculator. So then we can return it to our DIN. Great. Once we have our DIN, we can then initialize and ask for a voltage. So if we put, we could put DAC, we could put the write update function. So if we use channel A for this, it's asking us for our data. We can then replace DN into here. What does it return? It returns the status. So if we click return, status, so return put status there. And I think this returns a status update. So status, initialize it here. Then we could put a simple if So we expect 1 if there's not. So if it doesn't equal to 1, we can put, we could put some form of error handling here, but maybe we just wanted to know if we do it through putty or something like that. So if we put char UART string, so we're giving ourselves a buffer here, and let's say I just want, I don't know, sprint. So we say part through this string, and then we say failed to update. Maybe that's what we want to put here. Failed to see if we can probably get the syntax right for this. Yep. Then we could put the how UART transmit. So this is our handler we're putting through. What's the data? We could put UART string str length because it's just, well, then the timeout we can put, we just put the max delay on that. Put our close bracket here. So we are expecting, so we want an output voltage of 2, we've set our gain, what we have programmed in our begin function. Our internal reference is 2.5. If we build the program, we've run into some errors, running unused errors because I have fat fingers. 0 errors, 8 warning. I think we have to include a math. So after fixing all those errors that I found, just reinitializing, putting things in the right place really, like reinitializing these in the global, not in the main part of the code. Things like including the right libraries, here for what we need, all that really, nothing much. So if we grab it, so I've connected my device. Connected my device up here, you can still see it's at 2 volts from previously reflashing it, but I've built I'm gonna run it. It's gonna ask for things. We could just use the standard appliances. We're not too fussed about it. We'll see the device has started flashing. We're gonna see it going off. And yeah, we can see it's still showing 2 volts, which is what we expected on here. So if we change this to 1 volt now, again, build it, rerun our program, you can see it's changed to 1 volt. Now, I'm not too sure if it works for decimal, but we can have a try here, and if not, then it's something I need to fix, isn't it? So you can see it hasn't, because the calculation expects a in. So if we go back to our DAC here, and we go back here, and let's say we want a floating value, and again we need to go over here to the D in calc. We said we want a float. Yep, save those, go back to our main, we rebuild it again, has 1 error, it's fine. We flash our device and we get 0.8 on the output. Let's see if we could do 0.81, 0.81 output. Absolutely incredible. So you can see here that we've got a working driver library. I've shown you how you can make use of datasheet, how we can actually program this, things we can do, what we can do also. So I expect if I didn't put something here, maybe it would have given out of an error value or something we could not do. But let's say we put it to the 3 volts, see what it will give us. So it's given us 0.5 instead, which is not what we wanted, but we guess it's beyond the reference voltage that we have assigned. It can only go up as high as the reference voltage for this. So if we put 2.5 again, or the first time, we should get 2.5 on the output. So if we go back to 2, we get 2 on the output again, which is fantastic. Seems we cannot go above whatever we have set. So let's keep seeing if we can, see if we get 2.5. No, we can't. 2.4 maybe. So we can get up to 2.4. We can't really go as max as our reference voltage, but to know we can get quite close to it is very good in itself. So we have these here. We've been through a lot of what we can do. We've initialized it. We've shown you how to initialize it. We've shown how to do some calculation. Write a basic driver to get these things working, and a lot of this is just patience. There will be times where it doesn't make any sense and whatnot. You do have to just kind of bear through it, but There are many ways to write this. This is not a set way. It's something that I like to do, and I'm still learning and trying to improve upon things. But it's always useful to try and include as much information as you can to make it easier for yourself as well. Other people who may be reading this, but really good code would speak for itself. So let's take that into account there. And again, we could do a bit more to improve this, like such as improving the status handling, the error handling, show what errors have actually occurred. So if we put a bunch of ifs, maybe there's a better way to do this. We could put bunch of if statements here to say return the error that okay, the error persisted at the reset update, the gain set, things like that. We can put a lot more advanced error handling into it instead of just overwriting each other. So that's it. The drivers will be in the description. You can find on the GitHub. Please pull it. I will also include the design files that I used to make the breakout board, so please feel free to download, use it. This is what I used for this practical application, so please feel free to use them as you would.